Okay, so far we've given basic definitions of HMMs. I've just described how to estimate the parameters of an HMM. So you basically know everything there is to learn a hidden Markov model from a set of training examples. The final critical problem is, how do we apply this model to new test data sentences? And this is where we see the Viterbi algorithm come into play, which is a very famous algorithm. It's an example of dynamic programming, a critical idea from algorithms in computer science, and it's really a rather beautiful way of applying these models to test data sentences. So what's the problem that we're left with? It's the following. So we have some input sentence, x1 through xn. For example, it could be the dog laughs. And this is a new sentence, it's a new test data sentence, and of course I'd like to map this to a sequence of tags, for example, dnv. And to do that, I have my model. So this probability is defined by an HMM through the parameters estimated from a training corpus. And the task is to find the highest scoring tag sequence under this model for this particular sentence, x1 through xn. Okay, so again, S is going to be defined to be the set of possible tags. Let's say for the sake of argument, we just have these three tags here, dn and v. And so we're going to search over all valid tag sequences where yi is an S for I equals 1 to m, and yn plus 1 is equal to stop. We're going to assume that P takes the form I showed you for a trigram HMM. So this is this structure again. So just to recap, I have a product of Q terms from I equals 1 to n plus 1. Remember, yn plus 1 is always equal to the stop symbol. And then I have a product of E terms. So this is going to be terms such as E of the, given that I have determiner as the tag. So a first critical thing to realize, and a critical motivation for the Viterbi algorithm, is the observation that brute force search is going to be hopelessly inefficient in this scenario. And by brute force search, I mean search through all possible tag sequences where we simply enumerate each tag sequence in turn. Let me illustrate this with an example. Say again, we have the dog laughs as the input, so that is x1 through xn in this case. And let's say that S, the set of possible part of speech tags, is of size just 3, so we have D, N, and V, for example. Then I can list all possible tag sequences. So here goes. We have D, D, D stop, D, D, N stop, D, D, V stop, then DN, D stop, and so on and so on. Okay, so each valid tag sequence simply has one of these three tags, three possible tags at each of these positions, followed by the stop sign. And so we could conceivably just go through each of these tag sequences in turn. For each tag sequence, evaluate the value for P. So for example, we might find that this is 0.3, this is 0.01, this is 0.0001, and so on. I'm just making these numbers up. So we could just simply list all these possible tag sequences, apply the model, or the form of the model, to calculate these probabilities, and then return the highest one. Just say this one for the sake of example. The problem with this approach is that the number of possible sequences grows very quickly with the length of the sentence. So in this particular case, I have 3 to the power 3 possible sequences, because there are 3 choices here, the choice of the first tag, the second tag, and the third tag. and each of those choices has 3 possibilities. So in the general case, we have the size, the number of tags, the size of the set S, raised to the power n as the number of possible sequences. So the number of possible sequences obviously grows exponentially quickly with respect to the sentence length n, and for any appreciable value for n, say n is equal to 10 or 20 or 40, this number quickly gets very, very out of control, and it becomes hopelessly inefficient to do brute force search. So if we go back to this slide, the critical thing we're going to leverage in getting around this problem is that our probability distribution takes this form, and critically, these trigram parameters only depend on subsequences of length 3. So this model has a particular structure, and that will actually allow us to do search for the most likely tag sequence to solve this problem much, much more efficiently than brute force search. Okay, so now let's give some definitions underlying the Viterbi algorithm, which will be the efficient algorithm that solves these problems with brute force search. So I'll define n to be the length of the input sentence. So I have some input sentence x1, x2, x3 up to xn. And then a central definition is going to be this function r. So r is going to take a sequence of tags as input. So we always have star star as y minus 1 and y 0. These are the start symbols. And then we could have some sequence of tags for y1, y2, y3. And so k is the length of the sequence. In this case, k equals 3. So r takes in a sequence, such as star star dnv, and basically calculates its probability under the HMM using what is basically a truncated expression. So we just have the first k terms, a truncated version of the expression we saw for full HMMs. So I have product I equals 1 to k over these q parameters, and a product from I equals 1 to k of these emission parameters. And so this is essentially a probability of just this sequence, which is of length k equals 3 in this particular example. Now we're going to define a dynamic programming table. So pi k uv is going to be the maximum probability of a tag sequence ending in tags uv at position k. Actually, to be completely precise, we need a couple of other definitions. So I'm going to define s sub k for k equals minus 1 to n to be the set of possible tags at each position k. So again, if we think about this input sentence, x1, x2, x3 up to xn, and let's say s is our set of possible tags, say d, n, v, p, then at any of these positions, 1, 2, and so on up to n, we have 4 possible tags, d, n, v, p. And at positions 0 and minus 1, we have a single possible symbol, star. And these definitions reflect that. So s minus 1 is equal to s0 is star. So the set of possible symbols or tags at positions minus 1 and 0 are just the star or start symbol. And for any k in 1 to n, s sub k is equal to s. So it's the full set of tags. So this notation will just make things cleaner when we give the full definitions. Okay, so pi k uv. K can take any value in 1, 2, up to n. U takes any value in sk minus 1, and v takes any value in sk. So this is going to be the maximum probability of any tag sequence ending in tags uv at position k. More precisely, pi k uv is, here I have a max over all sequences, with k tags, y1 through k, preceded by y minus 1, y0. These are both star, always assumed to be star, such that yk minus 1 equals u, yk equals v of this r function I've shown you here. So that's the formal definition. Let me give you a particular example on the next slide. So let's number these words. So 1, 2, 3, 4, 5, 6, 7, 8. And let's say we consider the entry pi 7 of P and D. What does that correspond to intuitively? So I'm going to fix these two tags here to be P and D. And let's just assume that our set S is equal to D, N, V, P. So if we look at any of the preceding positions, we have 4 possible tags at each position. So we have all of these possibilities. Let me just write these out. And we always have star, star as these two start symbols. And so there are many possible different sequences of tags which end in PD at positions 6 and 7. For example, I could have D, N, V, P, 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 D. That's one possible sequence. And there are many others. Each of them will have a probability which is calculated by multiplying together the trigram probabilities and the emission probabilities, these Q terms and these E terms. And pi 7 PD is going to be the maximum probability for any of these tag sequences which ends in tags P and D at positions 6 and 7. So now let's give a recursive definition. The critical idea is going to be that these pi values can actually be calculated efficiently using a recursive definition which is given on this slide. So firstly, the base case is going to be say that pi of 0 star star is equal to 1. This basically just reflects the fact that every tag sequence starts with star star at its very beginning. And then we have a second definition which is more interesting. This is the recursive definition. So it's saying for any value of k, for any u in sk minus 1 and v in sk, so remember k can take any value in the range 1 to n. U is always going to be in the set sk minus 1, so this is going to be one of the tags which are possible at position sk minus 1. And similarly, v can take any value in sk. Remember, sk is the set of possible tags allowable at position k. And so what do we say? We say that this is equal to the max over all tags at position k minus 2. So again, this is the set of possible tags at position k minus 2. We take a max over that. We compute pi of k minus 1 wu, and then we have q of v given wu, and then we have e of xk given v. On the next slide, I'll illustrate an example which justifies this recursive definition. It is recursive, though, because this pi value depends on a set of previous pi values, the pi values at position k minus 1. And so we have a recursive definition where we're defining the pi's in terms of other pi's, more specifically pi's at position k minus 1. So this is rather abstract. Let me describe exactly how it is justified.